For the sixth proposition of Book 2 of Euclid's Elements, if a straight line be bisected and a straight line be added to it in a straight line, the rectangle contained by the whole with the added straight line and the added straight line together with the square on the half is equal to the square on the straight line made up of the half and the added straight line. So basically, if we start with some line, the line AB, and we first bisect it so that we know AC and BC are equal to each other, so we're given this piece of information, and then we're going to add some portion of a line, this line BD, in a straight line with the line AB. So BD is essentially just an added portion to this line AB. And what we're trying to prove is that if we formed a rectangle from the line AD, so it's our starting line with this portion added to it, we want to form the rectangle AD and BD, and if we add to this the square on BC, and what we're left with is this square on CD. So that's what we have to prove for this video, but if you want to look at it in a more algebraic way, you can call this A, so that would make this A as well, and this can be called B. And what we're trying to prove is that if we take this entire line AD, so that would be twice A plus B, and we multiply it by this short section, BD, which is just the letter B, and added to this is the square on BC. So the square formed by A, and all of this is equal to the square on CD, which is just A plus B, and we have to square that. So proving this geometric statement also proves this algebraic statement. So to start this proof, let's first construct a square using the line CD. And I've labeled this square as CDFE. And we can construct this square because of Book 1, proposition number 46. And from here, what I'll first do is to connect the points D and E, and now we can construct a line parallel to the line DF, but through this point B. So we want a parallel line to the line DF, and we can label both of these points. We can call this H, and then this can be called G. And now through the point H, we want to construct a line parallel to the line AD, but also through this point A, we want to construct a line parallel to the line DF. So let's construct both of those. So now that I've finished constructing this figure, you can see I created a line parallel to DF over here, this line AK, and this line BG is also parallel to DF. And then we constructed the line KM, this line here, that's parallel to the line AD. And we can construct all of these because of Book 1, proposition number 31. So at this point, we need to focus on specific parallelograms. So let's first start by looking at this parallelogram AL and its relation to this parallelogram CH. So notice they have equal bases. The base AC and BC, these are equal to each other. But we also know that these parallelograms start and finish on the same parallels. So they start on the line AB, and they finish on the line KM, which is parallel to AB. And because they have the same base and they start and finish within the same parallels, we know that these two parallelograms are equal to each other. So we can say that the parallelogram AL is equal to the parallelogram CH, and this comes from Book 1, proposition number 36. And next, let's take a closer look at this square here, this CDFE. And we have this diameter here that's essentially bisecting our parallelogram, or our square. And what we know is that if we focus on this parallelogram CH, and this one HF, that these are both equal to each other since they're complements about the diameter in this parallelogram. So we can write that CH is equal to the parallelogram HF, and this comes from Book 1, proposition number 43. And through common notion 1, we can also say that AL is equal to the parallelogram HF. So this is due to common notion number 1. Things which are equal to the same thing are equal to each other. And from here, with this equation, let's add. So we can use common notion number 2 to add to each side of this equation the parallelogram CM. So we're adding this entire parallelogram here, which we can call CM, and on the left-hand side, so we start with AL, and we're adding all of this to it. So now essentially we just have a bigger parallelogram, and we can call that parallelogram AM. So at this point, we have that the parallelogram AM, so the right-hand side of our equation, we have this parallelogram HF, and we're adding the parallelogram CM. So we have HF, and we're adding CM to it. So now we have this nomen, and we can just write it as the parallelograms HF and CM added together. And from here, it's important to remember in the last couple videos, we talked about how this quadrilateral and this one here, since they're on the diameter and they're within a larger square, then both of these shapes here, these four-sided figures, these are each squares. And we can use that information since, let's consider this rectangle AM, this quadrilateral. And we know that it's formed, or it's contained by, the lines AD and DM. But since this shape here is a square, then DM is simply equal to BD. So let me write that DM and BD are equal to each other. And so this implies that the rectangle AM is contained by the lines AD and BD, since BD and DM are equal. So we can put BD here. And to this equation here, let's add this square here, this LG, to each side of this equation. And we can do that because of this common notion number 2. We're just adding the square LG to each side of this equation here. So on the left-hand side, we have the quadrilateral AM plus the square LG, and this is equal to, so we have this quadrilateral HF and the quadrilateral CM, and we're adding this square LG to it. So now we essentially have this entire figure here, which is just a square. And this is the square formed by the line CD. So we can just say that the right-hand side is now just the square on CD. And notice we pretty much have our proof now, since if we compare what we were trying to prove to what we have, this rectangle here on AM, this is composed or contained by the lines AD and BD, which is exactly what we want. So we have this part of the equation we're seeking, and this square on LG. So let's go and take a closer look. We're looking at this square here. And this length LH, this is going to be equal to BC, because within parallelograms, opposite sides are equal. And we already know this is a square, so this square is essentially formed by the line BC. So this square on LG is just the square formed by the line BC. And these are both equal to the square formed by the line CD. So we have everything that we were seeking, and we can end this proof with QED.